Good morning. Let's get started. So today we're going to talk about information retrieval system evaluation, which is essentially about how we can compare two systems or multiple systems and determine which one is performing better. Or if you make a change or adjustment to an existing search engine scoring function, how can we determine whether it has been improved or not, right? So that is evaluation. So in this lecture, I'm going to talk about the notion of evaluation and the notion of relevance. And then there are two categories of information retrieval systems I would like to cover when it comes to evaluation: the evaluation of unranked retrieval and then the evaluation of ranked retrieval. Ranked retrieval is essentially how Google does the search result, right? So you rank the result and then how good the ranking is. There will be supplements in the end about test collections and result presentation, but we are not going to cover everything. We are going to just come across the basics of retrieval and some classic metrics, evaluation metrics that we should consider when we evaluate IR systems. So let's take a look at the basic question about evaluation. So what is evaluation and how can we determine whether something is doing better or worse, right? So which is better? And so let me give you user a kind of a daily example. Like you are trying to purchase a car or you are comparing cars to determine which one is better, right? Mercedes-Benz versus a Toyota, right? So this question is kind of vague. What do you mean by which is better? Does it mean which one is faster and why, right? So perhaps you are interested in which one actually can drive faster. Maybe one car sounds faster, right? By hearing the revving of the engine, but that is subjective, right? The sound of the engine is just one factor. It's not directly associated with how fast the car is. So ideally, you may put the cars into a test, into a race, right? Perhaps you can test the car and then see how fast, right? The Mercedes-Benz can get from 0 to 60 miles, right? Is it like 5 seconds or 10 seconds, right? So in that way, you can determine whether it is fast or not. Sometimes maybe in a different scenario, perhaps you are interested in, which one is more reliable as a commute car, right? So if you want to use a car to commute, you don't really care about how fast it drives, but how reliable, right? It's not going to break down on your way to work. And so there are different questions to ask in terms of which one is better. But if you want to focus on the question of which one is faster, then let's zoom in on this question and determine how we can evaluate the two cars here and determine objectively which one is better. And so in order to make this really objective and a fair comparison, when you let the car, give a chance for the two cars to compare, you need to compare them on a fair ground, which means they need to go into the race on the same track, right? So you are going to let them race on the same track, have the same finish line, right? And then you can use the same timer or stopwatch, right, to time how long it takes from the starting line to the finish line, right? So that is the fair comparison. And so you see in this analogy, there is this notion of the same track, the same finish line, and then the same timer or the same evaluation metric and protocol. I hope this makes sense. And then when all these translate into evaluation of IR systems or search engines, it's exactly the same. And so this whole tradition of text retrieval conference, by the way, text retrieval conference is really a major conference for research groups and even companies to participate in the different competitions so that they can compare their results and their algorithms. And so they follow the same idea of the same track, same finish line, and then same timer. So for example, in the text retrieval conference, there are different tracks. And so these tracks can be the traditional ad hoc retrieval, the web track, focused on web information retrieval like web search engines, spam track, focused on spam filtering, or even medical and legal track focused on very different type of data and search that type of data, right? So different tracks for different purposes, and then the same finish line because they are going to establish the same gold standard or ground truth so that everyone, the results from these different systems can compare to and say whether you make the correct prediction or retrieval versus incorrect, right? So the relevance base is the same. And then they also follow the same procedure and protocol and even specific evaluation metrics. And these are, in a sense, the same timers or stopwatches that you use to do the evaluation. And so we are going to get into some of these, such as precision recall and so forth, when it comes to evaluation metrics. But again, the same ideas follow. Okay, same track, same finish line, same timer and measure. So with that in mind, let's look into IR evaluation. And when we talk about evaluation, it's very important to talk about what is the thing that we are used to judge how good a system is. And that is the notion of relevance, because the main objective of information retrieval system, is to help people find relevant information. Think about you as a user. When you go to Google, you want to find information that is relevant to your need, to your task at hand, right? So we want to help people retrieve relevant information with an IR system. And this is kind of a breakdown of components involved in an IR system. And so I want to split this diagram into two halves. And one is on the system side, which is about the representation of documents, the data. Like for Google, there is a representation, the whole algorithm to index documents, web pages, right? And then there's also the representation, hopefully. Let me see if I can pull my, actually no. Let me just very quickly use my Presentify, which is a great tool that I use to annotate. Okay, so you see this part is the representation, okay, of the documents or web pages for web search engine. And then on the system side, another component is really the representation of your query, right? You type in a few keywords. How does the search engine interpret your keyword and represent it so that both representations, the document representation and the query representation, can come together, and the system will be able to score the documents and provide a ranking or matching, right? So, and then the result, the output of it is the result, the output. It can be a ranked retrieval, it can be unranked retrieval. For Google, it's just a sorted list of pages that are potentially relevant to your information need, okay? And then, of course, and so that is on the system side. On the user side, right, there are documents or domain, right? So documents represent the domain, like, okay, the web domain is web pages. The medical domain can be medical records and, sensitive data, right? So depending on which area you are searching on, the documents will be different. Users' information need are represented by the topics, okay? So these topics are in fact your queries, your information need. Like, what are you looking for as users, right? So these are regarded about user and domain, right? And so in the end, between the user information need and the documents, right? There is a potential association that between some documents that are relevant to that specific topic or information need. And so certain relevance assessment can be done and establish the what we refer to either as a relevance base or recall base. Okay, and that can be used to evaluate, right? Remember, this is the result from the system, and so and then this is the really the ground truth, right? The recall base or relevance base that will be used to evaluate how good the result is. And so there's a whole evaluation procedure to evaluate how good the result is, right? So that is kind of the big picture of this evaluation from the system and user point of view. So now we discussed various processes in IR, but how can we know the performance of an IR system, right? Which method is better? And again, when we say something is better, we need to be more clear about what we mean by better, right? Better in terms of efficiency, right? In the case of two cars, it can be about how fast they drive, right? So efficiency or fast, is an important angle here, but it's really not the focus in our IR evaluation. This is an important, like Google, it has to done the job fast, right? Within sub-seconds, it should retrieve the results. Otherwise, like if it takes a minute or even an hour for Google to give you the result, you probably will go away by the time, right? But this is not a focus in this lecture. The second point of view is the effectiveness, which is going to be the main focus in this lecture. Does the IR system retrieve information useful, interesting, relevant to the user's information need or not? Right. So this is the main topic today. And then in addition to that, there is also, of course, user experience, right? Whether the experience is engaging, right? It allows you to refine your query and be able to really pinpoint what you are looking for. So, there's a whole user-centered perspective and human-centered computing point of view when it comes to evaluation. But that is not the focus here. Our focus is how effective is the search engine or IR system in bringing the relevant document to the user. So relevance is key in information retrieval. It is also key for IR evaluation. So, and so when we let's take a look at what I mean by relevance. Because relevance, when I teach this IR class, information retrieval class, many students confuse the notion of relevance with keyword matching. They think, okay, the more keywords match, the relevant the document is. This is totally incorrect. Okay, so let's spend some time, just maybe 1 minute or two, on this notion of relevance and make it super clear. So relevance is assessed, okay, relative to the information need. Okay, so it is the information need, okay, that really matters here, not the query, not the keywords that you type in. It's a totally different thing. Sometimes we may confuse, okay, we think our need is the keywords, which is not the case. The need is translated into a query expression, which in today's age with Google is just a bunch of keywords. But let me use this example here to explain that information need can truly be very specific and complex. So here is an example, like someone is looking for information on whether drinking red wine is more effective at reducing your risk of heart attacks than white wine, right? So maybe that person has a home family history of heart attacks, and he also loves drinking wine, right? And so he or she is making a choice to say, okay, let's stay healthy but still enjoy life and some drinking, right? And so that is the whole background. And of course, when this person goes to Google and put in the keywords, he's not going to write an essay, right, essay about that information need. Probably just a number of keywords such as a query like wine, red, white, heart attack, effective, right? And those keywords to represent the information need. And so here you can see the actual information need and the query is actually different, right? The keyword to some degree represent that need, but is not 100% accurate representation of the need. It's just a bunch of search terms. And so when we evaluate information retrieval systems, ideally, we should trace back and we should really go back to the user and say, what are you really looking for? Could you explain? Okay. So ideally, we should ask the user about what is really relevant, what is not relevant. In terms of the information need here, okay, again, this is the information need. This query is not the information need, it's just a representation of the need. Okay, and so when you evaluate an information retrieval system in terms of what is relevant, what is not relevant, you should go back to this, the original information need, to determine that. So I hope this makes sense. And it has nothing to do with, the keyword matching. Okay. So with that in mind, let's talk about the standard relevance benchmarks and how we establish relevance base. So this text retrieval conference that I mentioned, okay, or what we refer to as TREC, is established by the National Institute of Standards and Technology, which runs an annual conference for research groups and companies to participate to compare the result in different tracks. And it has a variety of standard or benchmark collections such as Reuters News and other document collections that are used to compare different systems. And then the retrieval tasks are specified, like they simulate user queries, okay? And then the establishment of the relevant base in terms of, okay, which document is relevant, which document is not relevant, is not, again, based on the keyword matching, right? Because you want to establish the relevance to the original information need. So it actually requires human experts to mark for each query and each document what is relevant, what is not relevant. Sometimes it can also have different granularity of relevance, such as not relevant, somewhat relevant, highly relevant, right? Things like that. And so, NIST actually, for some years they hire retired CIA agents to look at the original information needs, which is a whole paragraph or multiple paragraphs description of what the user is looking for, and then read the documents to determine whether those documents can satisfy the need, can be relevant to the need or not. Okay, so that is the procedure. And so the text retrieval conference is to support research within information retrieval community by providing the infrastructure necessary for large-scale evaluation of text retrieval methodologies. And this is, again, similar to the racetracks, right, where different car manufacturers participated in to showcase their engine, right? And so if that is a platform or infrastructure like a racetrack, Formula One, race competitions, if those are the platform to compare car engines, the text retrieval conference is likewise a platform, an infrastructure to compare search engines. I hope this makes sense. And so in this competition, in track, there are different tracks, right? Web track, medical track, legal track, and so you can participate in different tracks for different purposes. And so inside each track, there's one collection. Everyone compete on the same collection, right? Just like the same track, which will come with the same documents and topics. And then one measure, like, okay, the same stopwatch or timer to determine who reach, better accuracy. And then there is also the one gold standard, or the relevance base. Like all the documents and queries are evaluated by the same human experts, and sometimes they disagree and they will reconcile their results. But anyway, there will be a whole gold standard or ground truth that they compare to, right? That's one collection, one gold standard or ground truth, and then one measure, or one protocol, I should say, because sometimes there are multiple evaluation metrics, but they follow this exactly the same protocol. So let's talk about the protocol, and more specifically the evaluation metrics that we use to compare search results. And so the first set of metrics that I would like to cover here is regarding the effectiveness of unranked retrieval. Unranked retrievals are about retrieval in the context of retrieving documents versus not retrieving them. It's kind of binary, Boolean, right? Documents are either a match or not a match. Okay, so there's no ranking. And so in unranked retrieval, the most classic metrics include precision and recall. Precision, in short, is the fraction of retrieved documents that are relevant. So basically, out of the documents that match, that the system, your system, deems to be a match to the query, what is the proportion of them that are relevant, right? So, and then recall is kind of another fraction. It's a fraction of relevant documents that are retrieved. So basically, given this query, and then let's say, okay, among all the documents, 1,000 documents are relevant. Okay, so totally there are 1,000 documents that should be retrieved, right, to serve the user. But the system that you are looking at only retrieve 100 documents. So that 100 over 1,000 is a fraction of relevant documents that are retrieved. Okay, that is recall. And so if we have a breakdown of a confusion matrix such as what I show here, okay, so the columns here are about the gold standard, the ground truth established by human experts. Okay, and so two columns here, one is relevant, the other is non-relevant. And then for the rows, okay, these are the system result, what have been retrieved versus not retrieved. And you try to compare the two, right? The gold standard ground truth versus the system result to see how good the system result are compared to the gold standard. And so you can have a breakdown of true positive. Okay, so the true positive here is really those retrieved that are also indeed relevant. So if the system deems these documents relevant, and then they are deemed relevant by the system, but they are in fact relevant. So these are the number of documents that are true positive. Okay, they are regarded as positive as a system, and they are indeed positive in the sense of being relevant. Okay, and then of course among those retrieved, right, deemed as positive by the system, right, there are also documents that are not exactly, right, they are not in fact not relevant, and so they are false positive, right? The system thinks they are relevant, but they are actually not, right? So those are false positive. And then among all the relevant documents, okay, some have been retrieved, okay, those are true positive, but others have not been retrieved, right? So relevant document, these should have been retrieved, but the system thinks that they are not positive, they are negative, and so these are false negative. And then the fourth cell in this confusion matrix is the true negative. Like, okay, those deemed by human experts to be negative, to be non-relevant, and the system agrees The retrieval system agrees and put them as true negatives. And so true positive and true negative, these are correct answers by the system, and they are part of the accuracy calculation. Precision and recall, however, focus more on the true positive. And so mathematically, precision P is computed by TP, which is true positive divided by true positive here plus false positive. So basically divided by all retrieved documents, right? So true positive as a fraction of all retrieved documents. Okay, recall, on the other hand, the numerator is still true positive, but not over the all retrieved documents, but over the column here. Okay, over all true positive plus false negative. So this is the true positive as a fraction of all relevant documents. Okay, established by the gold standard, by the human experts. I hope this makes sense. So with that, let's take a look at an example. Okay, so we have the basic definition of precision recall. Let's take a look at an example. Just for the sake of discussion, let's make this super simple. 10 documents in here, in the entire collection. Okay, of course, Google is going to have billions, if not trillions of documents, but for the sake of discussion, let's make it 10 documents only. And let's say the user issues a query, and for a particular information need, okay? And of course, when he enters a query, the system is going to return a bunch of documents, right? That the system regards as relevant to that information need for the query. Now, let's say these 7 documents have been returned as relevant to the query. So now let's determine, let's suppose, okay, these are not the return documents. These are all relevant documents to the query. So these are the 7 documents. So let's say we hire human experts to go through the process for this information need to determine which documents are relevant. And they agree that these 7 documents here are indeed relevant to the query. Okay, and so with that, let's look at some results. Okay, suppose, right, you create our system and retrieve these documents, right? How can we calculate the precision recall? And so the procedure is like this. Okay, so it retrieved 2, 3, 4, 5. Right? And so let's create this confusion matrix just for the sake of discussion. And so again, the columns are the human expert evaluation, the ground truth, and then the rows are the system result. Again, 2, 3, 4, 5 documents are retrieved. And so out of these retrieved, through, if you compare to the actual, the ground truth, the true relevant documents, 2, 3, 5. Okay, these 3 documents are indeed relevant. So true positive is 3. And then of course 1, which is document 4, is non-relevant. Okay, so precision is 3 out of 4. Okay, so 0.75. So that is precision. Very simple. Now what about recall, right? Recall is again 3, but not out of 4 here, but out of the total number of relevant documents established by the human experts. So it's 3 out of 7, totally 7 documents that are relevant in the entire collection. So 3 out of 7 is recall. Okay, so again, if you want to look at the table here, is 3 out of this entire column, which is recall. Okay, so this is precision and recall. And these are the most classic metrics. But, you know, there are some relations that you need to understand when it comes to precision and recall. High precision, so usually if you have a system that you can adjust the parameters for, And when you adjust the parameters, you can try to limit the number of documents that you retrieve. So usually with fewer documents retrieved, you can have a higher precision. Okay, this is kind of a common observation. And by definition, okay, when you retrieve 0 documents, by definition, precision is 100%. Okay, this is just by definition. And you can also get very high recall, but very low precision by retrieving all documents to all queries. So in fact, if you retrieve all documents from the entire collection, right, you are going to get 100% recall, but precision will be very low. Okay, so in general, recall is a non-decreasing function of the number of documents retrieved. So the more documents you retrieve, the likelihood of having more relevant document in from the relevant documents will be increased, right? The chances of hitting 1 more or 2 more relevant documents just by increasing the number of documents you want to retrieve will hopefully increase, if not staying flat. So it's a non-decreasing function of the number of documents retrieved. In a good system, precision decreases as either the number of documents retrieved or recall increases. This is not exactly a theorem, it's just a general observation. And you see it quite common in evaluations. Okay, so now there's difficulty in using precision recall as 2 separate numbers, because when you have 2 separate numbers, it's difficult to compare, right? Maybe one system is doing better in precision, the other is doing better in recall. How can you say which one is better, right? So one way is that you can, we'll talk about a third measure. There's a combination of both. But also to kind of, when you calculate precision, is query by query. For each particular user query or information need, you can compute a precision recall. And so overall, you can certainly average over large documents across different queries. And so there are lots of difficulties when it comes to using precision recall as 2 separate measures. And so a combined measure makes sense. And so a very common combined measure is this F measure. So this may look scary, okay? But essentially, beta is just a parameter to control how much weight you want to give to precision recall. So PR here is precision recall. So PR is precision times recall divided by, a portion of factor of P plus R, right? And so let me, without going too deep into that formula, let me talk about a most common F measure or F1 measure. Okay, so F1 measure, this is based on the previous formula. By picking beta equal to 1, you exactly have this formula, 2 times P times R divided by P plus R. This is referred to as the harmonic mean of precision and recall. So it's a mean, okay, and it's a harmonic mean. It's what we refer to as a conservative average. And let me explain why this is a conservative average. Because there's a purpose to do this mean, because people may wonder, like, okay, why don't we simply do arithmetic average, like, okay, calculating the simple average between precision and recall. So for example, right, I mean, you may be wondering, like, okay, let's just take P plus R divided by 2, right? Why don't we just do that? Now, you will see this is problematic, okay, if you just simply take the average of 2. So for the sake of discussion, let me present to you this extreme example. Okay, let's say, okay, you create a retrieval system, and let's say you have no knowledge of information retrieval and you just want to create a dumb system, okay? And what the system does is that for for every query, you just retrieve all the documents. Okay, just retrieve every document and present all the document to the user. So you see, this system does nothing but present all the document to the user, which is not a good system, right? It's the worst system that you will ever have. And so if you look at the result of this system, so if you retrieve all the documents, you're going to automatically get 100% recall. This is basically 100%, right? Because you retrieve all the documents. Precision, in this case, will be close to 0, even though it's not exactly 0. Okay, so the average of 0 and 1 will be still 0.5, right? And so even this will actually be greater than 0.5. And so on the surface, this looks not bad at all, even though the system does nothing by retrieving all documents. Okay, so that is 0.5 performance. Now, let's consider a different system. Let's say you really do your best to come up with your scoring function and ranking and matching. And in the end, you achieve 0.5, 50% precision, 50% recall, which is actually decent. Believe me, there are difficult questions that 50% is not too bad. Okay, and so you actually put into lots of effort just in order to achieve 0.5 average. Okay, and so if you simply use the simple average, you see no difference between these two systems, right? And it's a very unfair comparison because this is not representative of the real performance of these two systems. So simple average is not going to do it. But if you use F, you're going to see the difference. So in this case, you know, when we calculate F in the first for the first system, because precision is so low, almost 0, when you take F, the value will be almost 0, if not 0. Okay, the F score. And then for the second system that you actually put some effort in it, okay, the average, the harmonic mean, the F score will still be 0.5. So when you use the harmonic mean, which is a conservative mean, it's going to give you a better picture of what the actual performance is. Okay, so obviously the second system is doing better, much better compared to the first one, because the first system was lazy, right? It does nothing other than returning all the documents. And so F, and one key characteristic with F is that if the two values are very different, like between precision and recall, F will become closer to the lower value. So it will suffer because of the lower performance in one metric. Okay, so it shows a better picture and is more representative of the true performance. And again, as I said, F is sensitive to the gap between P and R. And when you have a lower value in either P or R, F will be reduced closer to that lower value. Okay, so that is unranked retrieval. Okay, now let's talk about ranked retrieval, which is more common. Like, okay, in today's context, you are experienced with Google, which is produce a ranked list. And usually the top results are what you are interested in, right? You want to look at the first, and if there's a relevant document or page, it should appear at the top, right? Regardless of how many are the matches. And so ranked information retrieval is very common today, and so let's look into that. So how do you evaluate a rank result? So the system will return any number of results, and then by taking various numbers of the top return documents, you can produce a precision recall curve. So the first take to evaluate rank result, because rank result there's a sorted list, right? So you can start with, say, okay, let's start with just top 1 and top 2 and top 3 and top 4, right? You can gradually increase the number and then calculate precision and recall, right? And so you can produce a precision and recall curve. And so in this case, by comparing the curve, and let me, for the sake of discussion, right, let's say, okay, this is one curve here, and then I have another curve, okay, here. And so let's say this is system A, right? This is system B. And so you can tell that system B in overall is performing better because it's away from the origin, right? It's closer to the ideal point, right? Because this over here is precision 1 and recall 1, right? So this is the kind of the best that you can achieve. And so with that, whatever curve that is closer to the ideal point, or a bigger curve under the curve area, okay, is the system with the better performance. So by looking at the curve of the precision recall, just by taking different number of top results each time, you can compare the rank retrieval. So this is one way, using a plot. Now plot, of course, takes time to read, and so it's for one query. How do you average across different queries? And so this is kind of, there's some difficulty, right? So graphs are good, but people may want summary measures. So let's look at how we can summarize or average across the precision or recall, so that we can calculate a number for the rank information retrieval. So the first thing is one measure is called precision at K. Okay, so precision at a fixed retrieval level. So in the age of Google, I think it makes sense to calculate, for example, precision at top 10. Right? You want to see how good the result is in the first page of the search result. And so you can do that kind of calculation. Of course, this requires an arbitrary K number, and K10 is a very common number, but of course you can choose a different number depending on your domain interest. Like people really want to see the top 3 results, then you can say precision at 3. Okay, so that is one. There is also this 11-point interpolated average precision. So let me, instead of talking about this in abstract, let's go to a plot, right? So this is the precision recall curve. And so at 0 point, right, we can have a precision value. At recall at 1.0, right, perfect recall, we can have a precision value. And then in between, there's 0.1, 0.2, 0.3, 0.4. And so there are exactly 11 points, including, right, 0 and 1, where you can take the reading of the precision and calculate the average. But there's also a notion of interpolated, okay? So because we are not reading the exact numbers here. So for example, so for here, like if you're looking at 0.4, yes, this number may be a little bit over on the precision side, right? This is maybe, let's say 0.45, okay? We can read this number, right, as the precision and use it as part of the process to calculate the average precision. And then for this point, which is at, let's say, 0.2 or more, let's say this is 0.2, right? This is over 0.6, maybe 0.65, okay? Of course, this is just an estimate. So this is 0.65 at 0.2 recall, right? So you can, again, take this reading. However, for this point, okay, 0.1, okay? The reading here is like, again, it's like about 0.4 or maybe even 0.5. For the sake of discussion, let's just make it simple. Maybe let's say this is 0.5. However, this 0.5 does not really reflect the full potential of this system. Think about this. We know that in general, when recall increases, precision should come down. Okay, so in this kind of observation, we assume that at this lower recall level, there's actually a better potential for this system to achieve a higher precision. Okay, so at this particular 0.1 recall level. Okay, and so because you can see even on this plot, okay, at a higher recall level like 0.2, it can achieve 0.65. And so this number reflects the real potential of the system to achieve a higher precision number. Okay, and so supposedly at this 0.1 level, this should be higher than 0.5. And so instead of using 0.5 as the number, we're actually going to use the next number that is potentially, that is greater than this number. So we are going to actually use 0.65 as the current value for 0.1 recall level. So anyway, this is just a way to kind of get to see the best out of this curve and see what is the full potential of the retrieval system that can achieve at different recall levels. And so once you take the reading of the precision at each recall level for the 11-point precisions, then you can average them, okay, to calculate the average precision. In addition to those, there is also the mean average precision, which is the average of precision values obtained for the top K documents each time a relevant document is retrieved. So what you do is basically you are going to increase the number of top results one document at a time, but you are not going to calculate precision if there is no new relevant document. So you increase the number, and each time if a relevant document is included because of this increase, you recalculate the precision value. Okay, you avoid interpolation, but then when it reaches a fixed recall level, then you calculate the mean average precision. Okay, there is also the R precision, which is basically if you have 1,000 documents that are relevant in the entire collection, you are going to just retrieve the top 1,000 documents and compute the precision. Okay, and so think about this: if you retrieve 1,000 documents and all 1,000 documents are relevant, then in this case you actually achieve both perfect recall and precision. Okay, so this R precision is kind of taking into account the recall in this equation, but focus on precision. Okay, so I hope this makes sense. So there are quite a variety of different metrics that you can use based on recall and precision. So I don't want to spend more time on the different variations of these, but instead I would like to take a leap here and jump to another really popular evaluation metric for rank retrieval, discounted cumulative gain, or DCG. Okay, so and we're going to finish with this metric in this lecture. So what DCG does is to calculate the discounted cumulative gain at the specific position. Okay, and there is also the normalized DCG, which I'm going to discuss at the end. Once you understand DCG, you will understand what normalized DCG is. Okay, so let's say, okay, you are interested in the age of Google, right? Again, the first page is 10 documents. You want to evaluate DCG at position 10, right? Let's see how good the top 10 documents are. And then within this top 10, the benefit, the advantage of DCG, I'm going to show you the formula in a second, is that it still takes into account where each document is ranked. So if you want your evaluation to be better, you really want to boost the most relevant document to the top, right? So it really encourages early retrieval of the relevant documents. And DCG is the very popular metric in information retrieval research. And because I think it makes sense in the age of web search engines, I think early retrieval of relevant document is a must-have, right? So, and so again, the key characteristics of DCG is early relevant documents. When you can retrieve relevant documents early on at the top, the better the result. And so it takes into account different relevance levels. So sometimes like you have not just relevant versus non-relevant, but how relevant they are, right? 0, for example, for non-relevant, 1 for somewhat relevant, and 2 for highly relevant. DCG can also take these different levels of granularity into account. So let's take a look at the formula of DCG at position P. So P is an arbitrary number, and then so this is simply calculated by the relevance of 1. So basically, what is the relevance of your top 1 result? Okay, so you see this is as is. So the relevance of the top 1 result is not discounted in any way. Okay, and then starting with the second document, okay, you calculate like I is the rank. Okay, second document is going to be I equal to 2, third document I equal to 3, and so for each document there you want to look at whether they are relevant or not, right? So they say, okay, binary relevance, 0 for non-relevance, 1 for relevant. So if it's relevant document, you receive 1, but this value is discounted by the log of the rank. Okay, so imagine when you further down in the rank, I is going to be greater, and so the logarithm of I, of course, will still be greater, and so you are going to kind of discount the relevance by the rank. Okay, so even though you can still have some benefit of having a document, relevant documents down in the list, the benefit will diminish, okay, the further down the document is in the list. And so that is the equation. Let's take a look at an example. Again, we are going to use a similar example, similar to what we discussed earlier. 10 documents total in the collection. Given information need, these are all the relevant documents, right? So again, relevant document being the relevance score is 1, okay? So these are all 1. So when we look at the relevance of these documents, they are 1. And then some documents are not relevant, so this is going to be 0, right? And then 6, not relevant, 0. And then there's one more, document 10 is also 0, right? So these are the relevance scores. And suppose, right, you have a system that retrieves these documents, okay? Document 2, 3, 4, 5. In this case, in this particular order, right? Document 2 is number 1 at the top, document 3 number 2, document 4 number 3, document 5 number 4, okay, in this sorted or ranked list. Now, given this, we want to evaluate DCG at position 3. So we are really interested in the top 3 documents here. How can we calculate DCG? So the process, let me show you here. So again, these are the top 3 documents, right? Number 1, number 2, number 3. And document 4 is not relevant. Document 2 and 3 are relevant. Okay, so for the first document, rank 1, right, the relevance is 1, right? For the document 3, which is rank 2, the relevance is 1, and then the log of the rank, okay, log if it's base 2, and log I, which is 2, rank 2 in this case, is going to be log 2 base 2, and so still it's normalized by 1. Okay, so in this case, actually the second rank document is not penalized either. So the top 2 documents are also taken, the weight is taken as is. And then the third document is not relevant. So 0 divided by log 3, okay? And so in the end, the result is 2, okay? DCG at 3 is 2. Now let's, for the sake of discussion, let's compare to another rank, just to make sense of why this is important. So let's say, okay, the same retrieval result, but the rank is different, right? Imagine document 4 originally was at the rank 3, now it's rank 1. So now this is moved. Let's say this is the result in another system, okay? And so system number 2 produced this ranked list. Top 3, document 4, document 2, document 3. Even though the result look the same, the rank is different. So in the end, you will see that number 1 is not relevant, so it's 0. Number 2 is still relevant, and number 3 is still relevant, okay? And so this is penalized because even though you retrieve the same documents, but the ranking, the sorted, the order is different. And because you did not retrieve the relevant documents early on at the top, this is penalized. So the result DCG at 3 for this result is 1.6, which is lower than the previous number, which is 2. So in this case, system 1 performs the first example that we saw earlier, performs better, right? Because it boosted early relevant result at the top. Hope this makes sense. So I'm going to wrap up just with a couple of observations. So as you can see, we have DCG of 2, 1.6. So DCG values can be any number, can be larger than 1. And it's sometimes difficult to compare among multiple queries, okay? Because queries are going to have different behaviors and relevant document sets. And so it makes comparison very difficult. Ideally, if we can have a value between 0 and 1, such as precision recall, right? It makes things much easier because when it's 1, we know it's perfect. When 0, it's like the worst. And so here comes the normalized DCG, okay? Normalized DCG is essentially the DCG, what we have done earlier, divided by IDCG, which is ideal DCG. What is ideal DCG? Ideal DCG is the ideal scenario in which the best ranking is achieved. So in most cases, it's documents that are ranked in a purely decreasing order of relevance, like the most relevant document at the top, second most relevant, second place, and so forth. Okay, and so in this ideal DCG, that is the best result that you can achieve. And so you can use your DCG divided by the ideal DCG. And because no DCG can outperform ideal DCG, so this will make sure that the NDCG, the normalized DCG, will always be between 0 and 1. Okay, 1 being the perfect score, 0 being the worst. And so with this normalized DCG, you have a score that you can compare across different queries and systems, and makes it much easier to say, to kind of discuss and interpret your results. Okay, so I hope this makes sense when it comes to evaluation. So in this lecture, just to recap, we talk about evaluation in general, and then we look into different evaluation metrics from precision recall for unranked retrieval, and then continue kind of use or combination of precision recall for ranked retrieval, and then ultimately we arrive at this particular measure called discounted cumulative gain, or DCG, for ranked retrieval, which really encourages early retrieval of relevant result. So think about in the age of web search engines, you really want to see the relevant result, see what you are looking for at the top of the Google page, right? So I think that is what DCG is for, and then ultimately NDCG, that is the normalized DCG, enabling people to compare different scores within the range of 0 and 1. Okay, so that concludes our lecture for today, and we'll continue to discuss other factors related to information retrieval systems. So see you in the next one.